Come forward, come forward. Lots of seats in the middle. There are seats here. Good evening, everyone. It's really wonderful to see all of you today. I am Saurav Chatterjee. I am a faculty member of the Department of Astronomy and Astrophysics at TIFR. I will be taking you through this evening. On behalf of TIFR, I welcome you all to a very special lecture by Professor Brian Small Paul Schmidt. It is our great honor to have Professor Schmidt among us today. Before our exciting journey through the universe from the beginning to end, as Professor Schmidt puts it, begins, I request all of you to please settle down as quietly as possible so that we can start the proceedings. And please put your phones on silent. And I will now request our director, Professor Joram Chengalur, to say a few words, please.
Thank you, Saurav, and welcome once again. I'm delighted to have all of you visit TIFR for this public talk, which is, of course, part of TIFR's outreach effort. And as some of you may know, TIFR's outreach program is not just one of the country's oldest, but also probably one of the largest and most varied. All of our centers at Pune, Bangalore, and Hyderabad have very active outreach programs. Here in Bombay, we have the Chai and Wai series of talks every alternate Sunday held at the Prithvi Theatre in Juhu. And we have this very long tradition of hosting public talks here in this auditorium, the Homi Bhabha Auditorium. Please do check out our web pages and social media feeds for details of the next talks. Today, we are delighted to host a very distinguished speaker, the Nobel laureate, Brian Schmidt, Professor Brian Schmidt. You will shortly hear a more formal introduction of the speaker, but I'd like to take this opportunity to thank him for accepting our invitation and for coming here for this visit. Professor Schmidt's visit to India is part of the Ashoka University Lodha Genius Program, and I'd like to thank Professor Vijay Raghavan and others who helped organize this visit here to TIFR. So thank you again for coming, and welcome again to what I'm sure will be a truly delightful talk.
Thank you, Professor Chengalur. It is a great honor to host Professor Schmidt as today's speaker. Professor Schmidt is a distinguished professor at the Australian National University's Mount Stromlo Observatory. He was the Vice Chancellor of the Australian National University until last year, when he stepped down after about 8 years of service. He holds several positions of high-profile responsibilities. For example, he is the chairman of the board of directors of the Astronomy Australia Limited, which plays a crucial role in coordinating and managing all Australian national schemes and projects in astronomy. He serves one of the management committee of the ARC Center of Excellence for All Sky Astrophysics, commonly known as CASTRO. It is common practice to describe the speaker's academic journey and achievements during introductions. However, with Professor Schmidt, it is somewhat impractical to do so. It would just take too much time. And we would rather start hearing from him about the fascinating beginning and end of the universe. So very briefly, Professor Schmidt is a fellow of the Royal Society. He won the Shaw Prize in Astronomy. He won the Australian government's Malcolm McIntosh Prize, Harvard University's Brock Prize, the Posse Medal, the Venu Bapu Medal, the ARC Federation Fellowship, and the Laureate Fellowship. Oh, and by the way, he also won the 2011 Nobel Prize in Physics. So this he shared with Adam Rees and Saul Perlmutter for the discovery of the accelerating expansion of the universe. Professor Schmidt and his team studied exploding stars called supernovae in distant galaxies and discovered that they are moving away from us at an ever-increasing rate. This led to the discovery of an accelerating expansion of the universe, which back then was a very surprising result, with fundamental consequences in our understanding of the universe. Professor Schmidt has also been a force in science advocacy and public outreach. A significant portion of his Nobel Prize winnings went in donations to the Primary Connections Program, an initiative of the Australian Academy of Science that assists primary school teachers. He strongly advocates and shapes improvements in the public school system, in numeracy and STEM education. To paraphrase from one of Professor Schmidt's quotes, if the public school system erodes, democracy itself can erode away with it. Without further ado, I request Professor Schmidt to please take the stage. I also request Professor Chengalur to present Professor Schmidt a memento on behalf of the IFR.
Yeah, so thank you again for coming.
Yep, thank
Really
you.
looking forward to the talk. Yeah.
Thank you.
Stuff about the IFR.
Thank you.
Professor Schmidt for you, everyone.
All right. Good. Volume's working. I'm going to just have a little sip of water to start off with. So it is great to be back at TIFR. It's been a while since I've been here. And at some level, a lot's happened. And on another level, the universe kind of moves slowly. So today is a chance to talk to you about our current state of knowledge of the universe from the beginning to the end. And we'll have a chance to hopefully answer some questions at the end. But let's start at the beginning. So if we go through and think of the universe, Long ago, long before there were stars and galaxies, something happened. The universe as we know it was created, and it was hot and dense, and it was expanding in all directions. We call this time the Big Bang. I don't know why it happened, and I certainly do not know what happened before the Big Bang. So that's the head off. The first question that always asks what happened before the Big Bang? I don't know. Okay. So whatever happened, it happened. And what we do, we see everything after the Big Bang. And that is where cosmology tries to understand how the universe went from being insanely hot and dense until about 380,000 years after the Big Bang, we see the first signs of it in this image called the cosmic microwave background. Now, this is a picture in microwaves of the entire sky projected like you would normally project a globe, but we're projecting it from the globe being around us. So you can think, looking up at the roof, think of the whole hemisphere coming around like a globe and then projecting it like you would the Earth. So there you see all these little splats, and we'll talk about them later on. And those actually are bumps that eventually become tens of thousands of galaxies. But this is when the universe was 3,000 degrees, and it was glowing like the sun, slightly cooler than the sun, and it is that afterglow of the Big Bang. So we started really observational cosmology in the early 20th century. Edwin Hubble had access to the largest telescope on the planet, the Hooker 100-inch telescope that's still just outside of Los Angeles. And he decided to do something most people weren't doing. He was looking at little fuzzy blobs, which they called nebulae, because we didn't know they were galaxies yet. But we soon figured it out, and he helped figure that out. And he wanted to measure their distances. So measuring distances in astronomy is challenging because you can't just lay a ruler down between us and the nearest galaxy. Rather, you have to worry about how things appear. And this animation, you can kind of get the sense that the further away something is, the fainter it's going to appear. We all know that. And it turns out, using physics, we can calculate things very accurately this way if we knew exactly how many watts something is. The problem is we don't really know how many watts a star is, but you do the best you can. And what Hubble did is he went through and he looked at how bright stars were. And he just assumed, and this is right to an order of magnitude, that if you look at a galaxy, the brightest star in that galaxy is about the same as the brightest star in another galaxy. And so the further galaxy will have a fainter star than the nearby galaxy, and you can calculate the distance that way. The other thing he had to use was observations made by Vesto Slipher about galaxies, which were a real mystery, and these were done in 1917. And he was out measuring essentially the velocity of galaxies by what he thought was the Doppler shift. And the idea of the Doppler shift is, I think most of us get it in high school, is that if an object is moving away from us, its light waves or sound waves stretched. And so you can measure the stretch and figure out exactly how fast an object is moving away. In modern ways, it turns out we don't necessarily think of it as a velocity. We think of it as space itself. We'll talk about that in a second. So Slipher discovered the very odd thing that almost every one of these blobs, we call galaxies, was moving away from us. That was a surprise. There were a couple, like two, that were moving towards us, but you would normally expect things moving away, coming towards us. You would not expect everything moving away from us. That seems to indicate we're a special place in the universe, an unpopular place at some level, but it was a mystery. And Hubble solved that mystery by measuring the distances and making a very famous diagram. This diagram plots each galaxy and its distance from how bright its brightest stars are. So galaxies with faint stars are way over here, ones with bright stars over here. And then he plotted alongside it the redshift, or the velocity away. And what you see is there's a trend. The further away something is, the faster it's moving away. And in 1929, he proclaimed the universe is expanding. I'm going to give you a cartoon. I want you to watch this carefully and expand the universe. I just expanded the universe in my cartoon. Now I'm going to overlay before and after, and you can see why this cartoon tells you that Hubble could claim that the universe was expanding. Because when you look at nearby objects, shown by those circles, nearby things have moved a little bit as I've expanded the universe, and distant things, well, they've moved a lot. So the further away something is in an expanding universe, the faster it's going to appear to be moving away from us, just like what Hubble saw. Now let's do a thought experiment. We're going to expand the universe. Let's run it in reverse. So if we run the universe in reverse, things in the past are going to be closer and closer and closer, and eventually there is a time when everything in the universe is on top of everything else, the Big Bang. So the notion of a Big Bang kind of naturally emerges if the universe is expanding. You run the universe in reverse, and unless you do quite, I would say, crazy things, as we did for many, many years, you get a Big Bang. So as I said, we don't really know what the Big Bang itself is. There are many, many papers written on this, but we don't know how to test any of them. We can test things a little bit right after the Big Bang. But if you graphically put that thought experiment to paper or to PowerPoint, you essentially have the Big Bang, galaxies start moving apart, the universe is expanding apart. And right now, they have a certain separation. In the past, they were closer. And that dotted line there is the rate that the universe is expanding. It's essentially the velocity of the galaxy moving away from the other galaxy divided by its distance. And so if you can measure the slope of that line, you can extrapolate back and figure out when the 2 points are on top of each other, and that gives you the age of the universe. I thought this was such a cool thing to do. That's what I did for my PhD thesis. And so here I am in 1993, showing my PhD supervisor, Bob Kirshner, my Hubble diagram, as we call it now. And the value that I got for the age of the universe by extrapolating backwards was that the universe was about 14 billion years old. Now that was kind of an unpopular number in 1993. And time has demonstrated that I actually more or less got the answer correct, possibly for the wrong reasons, depending on who you talk to. But in the decade following my work, the Hubble Space Telescope was used and dedicated a lot of time to measure this precisely. And the correct answer is about that number. Certainly, we know it more accurately than I could measure it back then. So the universe is about 14 billion years old. I've just showed you a cartoon thus far. The universe actually has complicated equations that we use to understand it, and they're based around the theory of general relativity. So in 1907, Einstein had a revelation that acceleration and gravity were indistinguishable. The apocryphal story was that Einstein saw someone fall off a roof, and rather than trying to go get an ambulance, he had this revelation. I think he must be in the weightlessness because his acceleration offsets gravity. And I think that must always be an equivalence where you can't tell the difference of being in a rocket ship accelerating at 9.8 meters per second squared or being in a box on Earth that is accelerated by gravity at 9.8 meters per second squared. They're equivalent. Turns out this little subtlety took him over 8 years to solve. And when he did it, he figured out, as near as he could tell, that it predicted that the universe should actually have curved space. So published this in 1915, said space should be curved, and you could go out and test this with an eclipse. And the idea is the sun has a lot of gravity, so it will curve space around it. You look at the sky during an eclipse so you can see stars. So the stars will be bent. Their positions will have to travel through curved space, so they won't be where they are normally. Then you wait till the sun goes away, and you can look at that same field. It turns out you have to wait several months because the sun is kind of in that part of the sky. And you take another picture and you look, are the stars in the same spot? And it turned out they weren't, and they weren't by exactly the way that Einstein's theory predicted. Now, this discovery, which came in 1919, was on the front pages of newspapers around the world. This is the discovery that made Einstein famous. We always think that E equals mc squared and things like that made Einstein famous. Made him famous amongst physicists. This is what made him famous amongst everyone in the world, because from pure thought alone, aesthetics, he was able to come up with a theory which even to this day has never been shown to be wrong in any situation. Now that sounds like something that might occur often in physics. It doesn't. It is really, with the exception of Copernicus putting the sun at the center for aesthetic reasons of the solar system, it is literally the only time I can think of science being created out of a thought without trying to solve a problem. Normally science, you got a problem and you come up with a way to solve the problem. This was not there to solve a problem. It was basically, I think these things must be equivalent, and I'm going to spend 8 years of my life trying to figure it out. So that is the genius of Einstein. So Einstein's theory did a lot of things. It allowed Einstein to think about the universe. Because when Newton tried to think about the universe, he ran into trouble. If the universe goes on without end, which is what Newton was kind of thinking, the only way he could think about the universe, not having an end, there was no way for him to solve his equations for gravity unless the universe had nothing in it. And of course, Newton knew he was in it, so therefore it didn't work. There was no solution. Einstein, when he looked at how the universe behaved, such a universe behaved, it turned out his universe was in motion. And he looked around and said, "Oh, I don't like this. The universe does not look like it's in motion." So the first thing he did was to add another term, which he called, the cosmological constant. And the idea, as he realized, is the cosmological constant we think of these days as being energy that is part of space itself. So every part of space has the same energy. It's always had it, always will. And it turns out when you stick that into his equations, it makes gravity push on itself, kind of the energy pushes on itself. And so his reasoning was, I'm going to add just the right amount of cosmological constant to push against gravity that's pulling. I'm going to balance the universe out. Now, it turns out the solution didn't work because it was unstable, which means that if a butterfly flapped its wings here in Mumbai, eventually at the Andromeda Galaxy or beyond, the universe is going to be put into motion from that butterfly flap. So it didn't actually solve the problem. And he stuck on to that problem for a long time and eventually was quoted saying later in life that he was acting like a donkey, keeping on to it because it ended up being something that seemed irrelevant. All right, so it was eventually cast aside because it was not necessary. But it was always something that was allowed in his equations. So Einstein's theory of general relativity allows us to calculate how the universe will evolve in time. And it's not just this straight line I drew you. Well, actually, it can be. That line is just fine if the universe has nothing in it. So if the universe is empty, then the universe will just keep on coasting forever, like that. But if the universe has stuff in it, it's going to slow down. And if it has enough stuff, it will not just slow down, it will stop and go in reverse. So a heavy universe has a beginning, a Big Bang, and an end, the Gnab-Gib, which is the Big Bang in reverse. A light universe, it just keeps expanding forever, getting bigger and bigger forever and ever. Okay? So I told you that Einstein's theory also talks about the curvature of space. So the curvature of space is something that we don't have a lot of intuition on, because the curvature is happening in a fourth dimension related to time. And it is not something that most sane individuals can visualize. I have met people who say they can visualize 4 dimensions. You do not want to be one of those people, okay? Trust me. So the easiest way to think about this, I think, is triangles. Triangles add up to 180 degrees in a flat universe. So a flat universe is different than a universe that is curved onto itself, as opposed to a universe curved away from itself. So it turns out a heavy universe curves onto itself. The gravity actually bends space to make it finite. It's a universe, conceivably, if you had enough time, you'd head out this way, and you'd actually end up where you came back from. It's a universe where triangles add up to more than 180 degrees, just like on Earth. So if you measure the triangle on Earth, maybe not in this room, but if you connect Australia, Mumbai, and Antarctica, do that triangle, add it up, the Earth's curved, it adds up to more than 180 degrees. You can try that on a globe at home if you want to. Light universe, the triangles add up to less than 180 degrees. And the just right universe is one that has exactly the amount of matter necessary to be that open or hyperbolic geometry and the closed, the spherical geometry. That's what we call a critical density. It's also nice and symmetrically the same junction where the universe expands forever or where the universe eventually stops and goes in reverse. So a flat universe, the universe gets slower and slower over time and then eventually stops at an infinite time in the future. So a universe that has an infinite time in the future is infinitely big in space. A universe that has a finite lifetime has a finite volume. Time and space are connected. Now, a thought experiment one could do is one could measure how fast the universe is expanding and then look at very distant objects whose light takes billions of years to reach us, and we could compare how fast the universe was expanding in the past to the present. So in this case, if the universe is empty, its speed doesn't, its velocity, its expansion doesn't change over time. It's a straight line. The critical line, this dotted line, if you're on the bottom side of it, gravity wins. The universe is going to eventually stop expanding and go in reverse. The other side of that line, gravity loses, and the universe keeps expanding forever. Now, in 1994, just after I finished my PhD, 2 things happened. The first thing is that colleagues working on type 1a supernovae, a type of explosion of stars predicted by Chandrasekhar, they were able to figure out how to measure their wattage such that you could measure their distances to 7%. And this was about 4 times better than any other method at the time. And these objects are amazing because they explode, and 20 days after they explode, they are 5 billion times brighter than our sun, which means we can see them potentially all the way across the universe. They're also great because they produce more than half of the iron in the universe. So in your chair you're sitting in, that iron was probably exported from Australia, but produced in a supernova billions of years ago. Okay? So these things are quite important things, at least for the Australian economy, in the universe. I keep on telling the minister that he needs to invest in it. It hasn't worked yet. But anyway, another story. The other technology were digital cameras. So digital cameras have been in astronomy since the very beginning. The first digital cameras on telescopes were in the late 1980s. I got a consumer digital product in 1999 in Japan, and I was the first person I knew who had more than a megapixel digital camera. So we're more than a decade ahead, and a lot of the development indeed occurred within astronomy, as I'll show you in a little bit. But we had at the time 8 megapixel cameras, and we would make mosaics of 8 of them. So we basically had a 64 million pixel camera in 1995. Okay, that is actually a pretty respectable camera even today. But back then it was insane, because each night we would take, compared to this image right here, about 1,500 images on a telescope. Each one of those images has 5,000 galaxies, and every 1,000 years or so, a supernova explodes in one of those galaxies. And it's only by looking at hundreds of thousands of galaxies that we can find about 3 in all of these images. Those images added up to more than 50 gigabytes of data. That doesn't sound that much. But in 1994, 95, when we were doing this project, the largest hard drive you could buy was 1 gigabyte. So we had stacks and stacks of, and we didn't have that much money. So what we had to do was kind of daisy chain everyone's computer together and try to get it all to do stuff using software that I was in charge of writing. So to give you a sense, this is what a supernova looks like. I'm going to zoom in. That little dot, it turns out, there is a supernova, and we know it because we take 2 images. And then what my software had to write, which doesn't seem that remarkable these days because we have stuff that does this all the time, was to sift through everything and to find the new object that had appeared. Now this object, just to give you a sense, 5 billion light years in distance. It exploded before the Earth was formed. All right? So you really have this time machine going backwards. If you ever want to know about time machines, easy to go backwards, probably not so easy to go forward. So this is a time machine. Now, we were very lucky that when we were doing this project way back when, we ended up with a film crew that could come and give you a sense of what it was like. So I take you to Chile, pre-2000, on the Cerro Tololo 4-meter telescope. And as the night comes down, we have to be prepared because we get 6 nights a year on one of the best telescopes in the world, and that's more telescope time than anyone else gets in the world. So every photon is sacred. The sky goes by, we're testing, making sure every image, and you can see a much younger version of me and my colleagues checking the data. My software's running, looking for things, but it's not very good. We don't really have, I had a 2-layer neural network. I did not have a giant AI program. And so there's literally a sweatshop of people looking over all the stuff my software is putting up. And time is of the essence because we have to go and get spectra of them as well. And that's with the largest telescope in the world, the Keck telescope in Hawaii, which we have scheduled 36 hours later. We don't have any objects. That time is not going to be used for, it'll be used for something else, but not for us. Adam Rees, who won the Nobel Prize with me, Alex Filippenko there to receive our charts and to look for the, and to get spectra, which allow us to measure the velocity part of the equation with the Keck telescope. So I didn't sleep a lot. We did that for 4 years. And at the end of it, we got what was a diagram that I will show you. This is the real data. And on this diagram, we put it up just like that thought experiment that I showed you. In this diagram, we're looking at back in time. So this is redshift, but it's also time. So the time is at the top. And each supernova has an uncertainty. And the uncertainty is by the whiskers or the error bars. And so what you can see is as you compare the nearby and the distant objects, the first thing you notice is that the distant objects, not a single one, even the error bars, go in to this part of the diagram. The universe is not going to have a Gnab-Gib. I was very sad because I kind of wanted the universe to have a Gnab-Gib. It seemed it's got a beginning, it has an end. Wouldn't that be great? But the universe doesn't care what I do. The other thing we realized is that only a little bit of the error bars went into the yellow part of the diagram. On average, and with 99.95% certainty, which sounds good if you're a biologist, but not so good if you're a physicist, we could say the universe was expanding slower in the past and had sped up. So 99.95 is actually not bad for an astronomer, but it's not quite a gold standard. But fortunately, there was another team that we were competing with that we did not know, and they did not know that we were getting the same crazy answer. So there was a really interesting time when we first saw this data where I'm looking at it and going, what have we possibly done wrong? There's a mistake. We're going to have to figure it out. We went through, we could not make it go away. And at this time, the team we were competing with, Saul Perlmutter's team, had published a paper saying the universe was slowing down and quite fast. So they had a sensible answer. We had a crazy answer. And then at the beginning of 1998, we finally decided, well, it's a crazy answer. We're going to need to publish it. And then we got a hint that Saul's team had basically the same answer. And then in 1998, both teams published their answer. And we realized that both teams essentially had the same uncertainties or certainties. And so together we got an extra 9, so 99.995, which is about 4.7 sigma if you're a particle physicist. So again, doesn't cross the bear, but that's getting pretty serious. So we didn't say discovery, we said evidence, and it's for those papers which we were collectively given the Nobel Prize in 2011. And I think it's important to realize 3 people won the Nobel Prize, but 60-some people did the work. So if you ever see a member of our team, give them a hug because it's good that they feel the love too, okay? But it's an amazing thing to be part of a Nobel Prize ceremony, but I see them as a real celebration of science, okay? Of collective achievements. So what on earth would cause the universe to speed up? Well, Albert Einstein, of course, with that cosmological constant, gave us at least one answer, not maybe the only answer, but it's an answer. So it turns out without changing general relativity, we can make the universe accelerate, but we need, as I'll show you, 70% of the universe to be this energy that's part of space. So that is a big change to our universe. Now, when we made our first papers, there was necessarily skepticism, as there should be. And so it really took until we could see the problem from multiple angles that we could really believe this is what, and I'll show you some of that work here in a second, it's what you could really believe to be true. So to show you with Einstein's theory, what it says the universe will do, these are the different equation or graphs of the equations of general relativity if the universe just has normal gravity in it. Our experiment basically said, no, the universe is going to track like the red line. And it's worthwhile looking at this red line because dark energy is part of space. And as the universe expands, you and I, we become less dense, right? The universe is bigger, we stay the same, so the density drops. Dark energy doesn't do that. It's part of space. So as the universe gets bigger, it's just part of space. Its density is constant. So when the universe was born right after the Big Bang, the universe was really dense with us. But dark energy was irrelevant. It was at a tiny amount. But as the universe got bigger and bigger and bigger, at some point, about 6.5 billion years ago, it turns out, the density of the universe in dark energy suddenly rose above the density of the universe in our type of matter. So that crossing happened about 6.5 billion years ago. So when the universe was when the universe was dense with normal gravity, it was slowing down. And then 6.5 billion years ago, the dark energy was able to take over because the universe dropped its density of everything else below dark energy. Dark energy took over, and dark energy, it turns out, can keep pushing and pushing on itself in an exponential process. And I've been talking a lot to my students about exponentials because exponentials are really important. Exponentials happen so fast that by the time you realize they happen, it's usually too late. Okay, COVID is a good example, but monetary inflation is another one. It turns out this is the only exponential that won't eventually stop. Every other exponential grows so fast that eventually it runs out of space in the universe one way or another, and it breaks. Okay? If you're a rabbit population, all the rabbits die. They starve to death or something. But this one, it turns out it's the whole universe. There's nothing to break. It just keeps getting bigger and bigger. So it can go on without end. It's quite an amazing part of physics. So the detailed analysis of our data was that 70% of the universe was this stuff, the cosmological constant or dark energy. 30% was gravitating matter. That was the prediction. And as I said, people were like, oh, okay. Now it turns out it was looked at in a variety of ways, but the place that really, really nailed the experiment is the cosmic microwave background. This is sort of the Rosetta Stone that physics has handed the universe to understand what's going on. Remember, this is an image of the universe right after the Big Bang, 380,000 years when it's hot. The little bumps you see there are actually sound waves, acoustic, we call them baryon acoustic waves, but they're just sound waves. And sound waves are things we understand really well on Earth, and we can calculate to pretty much infinite accuracy. So if you think about throwing a rock into a pond, if the pond is made of water, it has a different splash mark than if it's made of honey. So you can look at the splash marks to try to figure out what the universe is made out of, because the Big Bang was like throwing a bunch of different sized rocks into the universe, the pond. And those waves splash about, and then you look at how many sound waves there are of different size. That's what the splash marks are, and you can compare it to theory. So this is what the data looks like. This is from the Planck experiment. And what we're plotting here is how many sound waves there are of different size. These are great big sound waves. These are really tiny sound waves. And you can see at about 1 degree, so that's about the size of your thumbnail at arm's length in the sky, there are a lot and lots of sound waves. That's what the theory predicts, and that's what the data shows. So each measurement here, you can see the uncertainties are so small, you don't really see, they're actually smaller than the dots in most cases. You can see the theory, which is pretty much based on what we said you would see in 1998, based on our measurements, has been seen in reality, pre-predicted, and the theory is actually quite amazing. You don't just get that from accidents. So, a catch. I haven't talked yet about dark matter. The theory does not fit that curve unless of the 30% of the universe that is gravitation, most of it has to be material that's invisible, that literally travels right through itself, does not interact. We cannot see it because the only way we know things exist is through interaction, and this would seem to not interact enough to see it. So it predicts very strongly that the universe is 25% dark matter, 5% atoms, and we get the other, we know that those are 25 and 5 because we can go through and, as I'll show you, use some geometry. Before I do that, I'll just say dark matter, we don't know what it is yet. I'll come back to it in a little bit. But our best guess is it's an undiscovered particle that's going through us right now, goes right through the Earth because it doesn't interact with anything. All right, so the other thing you can do with this experiment is to measure the geometry of space. Because if the universe is curved, it magnifies or demagnifies the sound waves. And from physics, we know exactly how many centimeters those sound waves are. And so how they appear on the sky depends on the geometry of space. And so like a spoon, which magnifies or demagnifies depending on which side of the spoon you look at, that's the different types of curvature, you can go through and predict how big the sound waves will be. And the prediction, it turns out, to 1 part in 1,000 is the universe is flat. That is that everything in the universe adds up to 100% of the just right amount, of the critical density. The one thing I haven't told you is that anything contributes to that material that adds up to shape space. So photons, neutrinos, matter, dark matter, and the cosmological constant. So everything in the universe adds up to 100%. So we can do some cosmic subtraction where everything adds up to 100%, to that critical amount of material to make the universe flat. We know that 25% of it's dark matter from the cosmic microwave background sound waves. We know 5% of it is atomic matter from that same experiment, leaving the 70% mystery matter that we discovered as being kind of the same thing. So it all hangs together, it turns out. And no matter which way you look at it, it would seem that the universe is a little crazy. 5% of the universe are the atoms that we know of in this room. Every Nobel Prize ever done, except for ours, is on that 5%. Okay? The other 95%, dark matter and dark energy, are things we cannot see here on Earth. We only see by their effects of gravity on cosmic scales. Now, if you're a bit of a cynic, and I know most of you are, you will be saying, Brian, if you've got to make up 95% of the universe, that almost certainly means you don't know what you're talking about. And I think that's probably a fair criticism. The way science works is you make predictions. And remember the prediction of the cosmic microwave background with those 32 bumps done perfectly. That's not an accident. If you change this model even a little bit, it doesn't work. So when you predict something in 1998 and a decade later it's seen to be true, so you pre-predict, that's a sign you understand what's going on pretty well. Doesn't mean it's perfect, but it means the basic idea is hanging together. So it is crazy. It is our best idea of the universe. But of course, we want to keep testing it. And so science works by continually testing and testing and testing. So where are we? Well, we want to know what dark matter and dark energy are. Dark matter, wouldn't it be good to figure out if it's a particle, to actually detecting the particle? So the hope is that, well, it'll go right through the Earth, just occasionally it would bump into something. So if that's true, one could imagine, for example, in the Large Hadron Collider, creating it. You crash things together, and every now and then you might make a dark matter particle. So the dark matter particle will go right out of CERN. You'll never see it again. But CERN has the ability to crash things together and then add up all the energy. And if something has left the building secretly, you know it's left the building because it adds up and says, whoa, there's some energy and mass missing. At this point, nothing. No sign of anything. Another way to do it is to hope that it will bump into something very rarely, like a neutrino does. So the best way we have this right now of doing these types of work is to take giant vats of liquid xenon, which is the heaviest non-radioactive inert thing there is, putting them in a mine where nothing else can get to them, and waiting for a dark matter particle to potentially collide with a xenon atom and go ping. They really almost do a ping. A phonon is made if that happens. So we have now many tons of xenon underground. We have waited several years. Nothing. No detection. The other place you might hope to find dark matter is in space itself, because space has huge expanses, and maybe if it's going to interact with itself or with something else, you'll see a sign of it. So we've had a couple false starts here, probably pulsars making things that we didn't understand. At this point, no evidence that is credible, in my opinion, of any signs of dark matter from anything other than gravity. So we keep working, but it's hard. So at this point, dark matter remains a mystery. Dark energy? Well, dark energy in some levels even harder, because there's no hope of detecting it here on Earth. There's literally a microgram equivalent in the entire volume of the Earth. It is just something that is very difficult to figure out how you might ever test in a laboratory the size of, even the size of the Earth. So the way we've been looking at it is trying to see, does it behave exactly like Einstein's cosmological constant? Is it constant for all time? Does it accelerate the universe exactly as Einstein's equations say? Because if it changes over time, then it won't exactly do what the equations say it will. So this is gathering huge quantities of data. So this is the current best data from supernovae released not too long ago. Actually, I lie. This is one about a year and a half ago, but it's equivalent more or less to the best ones now. But effectively, there is almost no signal here. It turns out, as I'll show you in just a second, there may be a little bit of signal right here, but I would say nothing, at least from my perspective, to get that excited about. Other methods of measuring distances have come as well, again from the cosmic microwave background. Those bumps turn out, I told you, make galaxies. And we can look at the galaxies today and we can see those same sound waves in the galaxies today. And so by literally looking and plotting millions upon millions of galaxies, we can go through and chart the size of the sound waves over time. So these are called baryon acoustic oscillations. We have galaxy surveys now that map the sky, and you can see that foam structure. Those are remnants of the sound waves there. And if you go through and do this over time, you see the acoustic signature in all sorts of galaxy surveys, and you've got how big it is relative to Einstein's cosmological constant, the black line. And people have gotten very excited in the last few months by this little deviation right here. Now, at this point, I'd like to see more data. It turns out exactly the same place where there might be a kink in the supernovae, but at this point, I would say, hold your horses, let's get more data. This is some of the first evidence that is not necessarily directly aligned to Einstein's cosmological constant. But as I said, I would be cautious and look to get more data. Another kink has also occurred, and that kink has come from my colleague Adam Rees measuring with increasing precision using the Hubble Space Telescope the Hubble constant. And the Planck mission with the cosmic microwave background, able, because it can do such an amazing measurement on those sound waves, it gives you how fast the universe was expanding way back in time, and you can then extrapolate it to the present time and see if they match up. And the extrapolation is formally very, very accurate from the cosmic microwave background. And you can see over the past decade, we seem to be getting two different answers. You get the Adam Rees and other people in the nearby universe getting that the universe is expanding slightly faster than what you infer from the cosmic microwave background. Now, Adam Rees and I were PhD students together. I'm 3 years older than him, so I'm sort of his academic big brother. And there is nothing in life I would love more than to show Adam that he's wrong. That's what a big brother's like. I have tried. I can't find any mistake in his work. I'm just honest. Doesn't mean it's right, but I don't see any issues, okay? So I think this is a serious issue. Am I absolutely sure? No. Am I 99% sure? Yes. So one of the things I'm working on is trying to measure distances in a completely different way with a different type of supernova that's independent from anything else. And that will be something over the next few years. I try to see if we can differentiate between the two models. But at this point, I don't have any idea, and I have not seen a credible way to fix this problem. And if you're thinking, as I thought, maybe the problem I just showed you of the universe not behaving exactly like the cosmological constant, maybe this and that can be fixed by the same thing. Well, not obviously. They actually seem to work in different directions. So maybe it's just mistakes of measurement, right? So one of the most likely things as scientists is people don't quite get their experiment correct. That may still be at play, but I'm beginning to get suspicious here. So it might be we're on the edge of a revolution of understanding where we have to substantially change some of the things I've told you today, okay? I wouldn't go home and say that yet, but it is a possibility. And then I remind you, as we spend all this time trying to figure out what dark energy and dark matter are, there's all these other amazing things going on. We have the square kilometer array, which is part of, we have the James Webb Telescope looking back to the dawn right after the Big Bang and seeing galaxies form for the first time. It's amazing stuff. We're seeing black holes, and LIGO India will help with this tremendously. Black holes merging together, indicating that the universe is full of black holes that are much bigger and frequent than we ever thought should be there. These are things we are yet to understand, but we're beginning to observe. We can go through and we can see giant supermassive black holes and actually directly image them in nearby galaxies. So this is what it looks like with the Hubble Space Telescope. But if you zoom in by another factor of 100,000, you get to actually see the shadowing effect of the black hole on the stuff around the black hole. So that little donut is actually something much more profound than it necessarily looks like. It is really showing you the shadowing effect of the black hole where light cannot pass through there. What we see is throughout the universe, even at very early times, there are black holes that are far more frequent and far larger than we can understand. And there are thousands of papers trying to figure out what might be going on. And I think these are exciting things we will figure out over the coming decade. Finally, the next generation of giant telescopes and the James Webb Space Telescope are allowing us to look into the atmospheres of exoplanets. And we can hope potentially to see signs of chemicals or essentially molecules that are signs of life. Now, I don't know what's going to show up. You've seen in the last few months claims of something exotic. I think those claims are maybe not as strong as maybe one might wish them to be, but there is, I think, an opportunity for us to go through and say, is life frequent or is it rare? And that's going to happen not in the next 50 years, but it's going to happen in the next 10. So many cool things to do. So one of the things I think it's worthwhile thinking about is, why do we do all this? Well, we do it, and I do it, because it's exciting, interesting, and it is something, this type of knowledge has bound humanity from our very beginnings. The stars were used as ways to understand when to plant. It helped create the whole notion of science. But our governments fund it ultimately because it's useful. And we should remind ourselves that. But the use comes from actually exploring and not knowing what we look for, building up knowledge. And in my own area of astroparticle physics, you can look at many of the key things that drive a modern iPhone as things we have contributed. The Wi-Fi is from Australian astrophysicist radio astronomers trying to understand how to look for evaporating black holes. The CMOS camera, well, that comes from a mission to Jupiter. The touchscreen in the World Wide Web, well, that comes from CERN. The GPS is making precision time clocks, putting them in spacecraft, and using general relativity to figure out where you are. Indeed, if you go through and look at all the basic science discoveries that go in to an iPhone, there are literally thousands of them over hundreds of years. So when a minister comes and says, let's just invent an iPhone, it's a great idea. It's just not the way it works. iPhones don't just invent themselves. They emerge from knowledge. And they emerge from all sorts of disparate knowledge and people who are learning that disparate knowledge. That's how the innovation cycle works. No one has figured out how just to go and do the good stuff. You got to put the hard yards in and advance knowledge. And from that knowledge, that sea of knowledge, innovators can pull out the useful things, put it together, and create prosperity for the world. So it is a highly interactive cycle of self-reinforcing. And our future? Well, we got about 1 billion years left on the Earth till our sun heats up enough to cook our oceans off. We've got about 6 billion plus or minus 1 billion years till the sun expands so much that the Earth is vaporized. And then there's the universe. Well, the future of the universe seems to be dark energy, with the caveat we may not understand it well at all. But if dark energy continues to behave the way we see it right now, then it keeps becoming, pushing the universe apart faster and faster, such that in the future, things move apart more quickly than light can travel through it. So a galaxy that we can see right now will put a piece of light, the light will try to travel through space, the space will expand faster and faster, and the photon will get stranded between the galaxy and today. Galaxies we see today, the light they emit, especially the ones that are about 10 billion light years in distance, the light will never reach us in the future. It gets stranded in space. And that gets worse and worse and worse as the universe expands faster and faster. So, unless the universe's dark energy suddenly disappears, well, we can expect the universe to, at an ever-increasing rate, expand, fade away, meaning future cosmologists like myself will have nothing to look at. Thank you very much.
I'm sure Prof. Schmidt will.
We'll take a few questions, but it's okay if you need to go up.
Yeah. So there are mics here, and please raise your hands. There.
I really want to thank you for an absolutely wonderful presentation.
Thank you.
I really learned a lot about some 75% that we don't know anything about. I still learned about it. But I have a question. I'm very into sound vibrations. I'm a film director. And I'm inspired by what we call NAD, which is the resonance from the sound vibrations, what is left with us after we hear the sound. So I was wondering if you, as a physicist, can take sound vibrations. Can you hear me? Yeah.
Yep.
So can you take sound vibrations as your starting point to explore further rather than light travel and all the other stuff? But sound vibrations is the beginning of the universe, was vibrations.
So the way science works is we start out with certain observations, and then occasionally we have to make some what we would call assumptions, founding assumptions, okay? So the sound vibrations in the universe, in our case, are caused by, we believe, quantum mechanics, okay? So the whole philosophy of science is creating effectively equations that hold together and make predictions, okay? So you would not start with sound. Now, that might be the answer, but you don't start with sound. That has to emerge as a solution. It's a philosophy that is different than other philosophies, okay? And so the scientific method is one where you kind of have to make it all fit together, make predictions. You don't impose something that you think. You try to do it in a slightly different way, okay? And sometimes you can impose, but then you have to calculate and see if it works.
But our rishis from way back, our sages.
Say it again?
The rishis, RISHIS, they used to meditate, close their eyes, and from the vibrations, they could understand the universe.
But it's a different philosophy than science. And so I think it's good to keep the philosophies separated unless you really have ways you think they're going to work, okay?
A sound scientist.
Yeah, so that's what science is about. And it's a philosophy, and we, as scientists, like the philosophy, but the reality is ultimately it's a philosophy that's self-contained, and it's different than other philosophies. And I make no ups or downs to say just science is very good at predicting things here on Earth, but it has limitations, right? And that's what we would.
One thing.
We will.
Yeah, we're going to move on. We need to move.
We'll move to the next
Sound
question.
science. Get a sound science.
Sorry, I can't hear you, but I'd like.
So the next question.
Yeah, he has a microphone.
Is
He'd like to do this
the
question.
yellow
Yeah.
shirt?
If there's an equal amount of matter and antimatter, then why don't they just cancel each other out and leave with energy? Then why is there density in the universe?
So this turns out to be a really big mystery. So right after the Big Bang are equations that emerge right now say there should be equal amounts of matter and antimatter. For every piece of matter created, there'll be some antimatter. And when matter and antimatter get together, they essentially create a big burst of energy, a photon normally. And so what we should have is a universe full of photons and nothing else. What we can do is we can count how many atoms are there in the universe and how many photons are in the universe. And it turns out there's about 1 billion photons for every piece of matter. So there is something in the equation that is wrong at 1 part per billion. And that is something when you go to university, maybe you can solve because no one's figured it out yet. Okay?
The next question goes to the gentleman with dark glasses.
Thank you, Brian, for your talk. It was wonderful. I just want to know if is it possible that the Hubble parameter could be time variable or different in different neighborhoods, and how would that reflect on the Hubble tension that you talked about?
I need to understand. So, what do you want to be time variable?
Okay, what I'm asking is it possible that the Hubble parameter
Yep.
is like time variant, or it's different in the different neighborhoods that you observe, right?
Okay.
So with that, yeah.
Yeah. So the big question, I'm going to rephrase it a little bit. So the underpinning assumption, which I would talk about in a physics colloquium, is that the universe is homogeneous and isotropic. Okay? And that's something you can test at some level. Clearly at the cosmic microwave background, it shows a high degree of homogeneity. When you get to the present day, there are variations which are factors of 30% would be a typical names with some much more concentrations. So there is an ongoing conversation, I would say, with probably 90 to 95% of people saying the universe acts as a homogeneous thing. There are people saying we think the bumps and wiggles we see today actually mess up the equations of general relativity, and so that the Hubble constant might be different depending on where you look. Okay, so I try to be as agnostic as I can in these things, and I would say I'm open to doing experiments that can test the inhomogeneity hypothesis. I think it's something we need to consider. I think it could be something that might explain, for example, the Hubble tension, if that's real. And that is the type of thing that could emerge from that. Do I think it makes the whole everything go away? Really, really difficult, again, to get the cosmic microwave background exactly in advance. It's gotta, that seems, it's not that you can't do it, but it seems unlikely. So I want people to do a lot better calculations in general relativity. I cannot understate how difficult it is to do calculations in general relativity if the universe is really lumpy. Now, that doesn't mean that's a reason not to do it. I'm just telling you it's hard and why people don't agree. Yeah, thanks.
Good. Boy in white shirt at the front.
Where are we? Oh, great, thank you.
So, is there a way to differentiate between dark matter and any other form of matter?
So the big issue of how we differentiate between dark matter and everything else is dark matter is invisible. So they have the same gravity as near as we can tell. So if I had, let's say, a kilogram of dark matter and I have a kilogram of you, the gravity would seem to be identical as near as we can tell. Okay. But the difference is the dark matter seems to be invisible, so it doesn't have pressure. So pressure, we know it makes sound waves, okay? So the sound waves in the early universe are made up entirely of the atoms. The dark matter just goes right through itself, and so it only acts by gravity. So we see it in a number of ways. One, in that the sound wave signature, you don't get the sound waves to be right. You got to have a mixture of things. But when we look at galaxies, we see that they have a lot more gravity than atoms in them. And it's like a factor of 6 or 7 all the time. We also see, in one case, big clusters of galaxies going through each other and the atoms smashing and making lots of X-rays. And then it would seem the dark matter has gone right through and made 2 clumps of things that we can detect through the process we call gravitational lensing that I have not talked about. But space is bent by gravity, and you can kind of see the space warped a little bit and warped a little bit, and you can see it would look like that the dark matter is there, has gone right through, and the atoms have crashed in the middle. So it kind of makes sense every way we look at it. There are some people who think dark matter doesn't exist at all. And we can test their theories. I would say at this point, they really struggle again to get the sound waves in the early universe to be sensibly measured. But again, we need to be open, looking at every credible idea, because it's a crazy universe.
Put the lady in there.
Now,
Thank you for the talk. I had this question that since dark matter interacts with the gravity, then is it possible to detect dark matter using gravitational waves?
so the answer is probably not. And the reason is that dark matter, the reason you can get gravity waves is you can make really compact objects like neutron stars. And neutron stars exist because the atoms or the quarks push, and so you get a structure that isn't a black hole. Now, dark matter itself is really hard to make black holes because it just goes through itself and you can never get it condensed down. It is possible for black holes to, hoover up dark matter over time. So, but it's got to be kind of close to a direct hit. So there's some dynamics there. So I wouldn't want to say it's impossible, but it's not clear to me that there's ever going to be a signature there at this point.
Gentleman, go back.
So it's an outstanding presentation. Thank you very much.
Thank you.
Though I'm a student of biology, I'm fascinated by astronomy and astrophysics. One of the commercial exploitations of antimatter has been the positron emission tomography. Am I right? So my question is whether any other antimatter has been exploited for medical use or any other use. And corollary to this, it is being said that banana is a good source of positron and emits about 15 positrons per second. I don't know how far it is true. If that is true, and 1 gram of positron costs double the GDP of United States. So if banana decay can produce positron at this rate, is it possible for producing a larger scale of positron? These are the two questions. Thank you.
Okay. I'm trying to think if there's anyone's figured out. I'm not going to. I think there are ways to use positrons to do some medical imaging, but I need to go through and think exactly how it works. You would normally use them because they're creative in a radioactive decay, like in a banana. And then when the positron is emitted from the radioactive decay, it runs into an electron right next door and emits a gamma ray, which you can detect. So in that way, positrons are used in medical imaging. But you're not going to just shoot positrons into something because they're really, really hard to contain and keep from creating a gamma ray, okay? So if you want to have contained gamma ray or contained positrons where they're not running into electrons, that's the stuff that's super, super expensive. Right now, there are positrons in a very small rate being created from radioactive decays in this room. They're everywhere. They're in bananas. They're all over the place. It's just that they almost instantaneously find an electron and create a gamma ray. Now, positrons are nasty, nasty things because gamma rays are nasty, nasty things. So you really don't want to be around a radioactive source that produces a lot of positrons is not your friend. And so I would say there are ways to create lots of positrons, just very hard to store them. And the way you store them is through typically magnetic confinement, where you can keep all the positrons on themselves. And we can even make like antimatter atoms and things these days, but they tend not to last that long. I had a friend who had a trap that kept a positron all the way, and they lost it in the Colorado Rockies. They were taking it from Harvard to Berkeley, and they lost it as it was sort of a party trick. So anyway, it is a very challenging thing to manage. So I hope I've sort of answered your question there.
So the question here,
Yeah.
in the middle.
Sir, as the universe is expanding because of dark energy. So I had read somewhere that because of the expansion, the fabric of space-time will tear apart in future. So what do you think about this? Like
I need you to re-say the question. I didn't quite
Okay.
catch all the parts of it.
Okay. Because of the dark energy, the universe is expanding.
Yep.
And in future, I read somewhere this that in future, the fabric of space-time will be tear apart because of the
okay.
over expansion.
So it turns out that if dark energy gets created a little faster than space gets created, it's not Einstein's cosmological constant, it's something else. And that will actually rip space-time apart. Now, a lot of people think that violates all sorts of various quantum mechanical conditions. I would say unclear, but it would certainly be an exciting way for the universe to end. At this point, I would say no evidence it's the way the universe is, but I wouldn't say there's much evidence against it either. So it's something we need to consider, and it would be an interesting way to rebirth the universe, because it turns out as space-time gets ripped apart, that almost starts looking like a Big Bang again. So, maybe there is a way for dark energy to rebirth the universe in a Big Bang.
I think there is a question there.
Thank you for your wonderful talk, Professor Brian. My question is regarding, you said in the early universe, matter created baryon acoustic waves, and you showed us a plot which had multiple peaks. I wanted to understand what those peaks specifically represented and like why are they multiple peaks?
Okay. So those peaks essentially represent reverberations. And so the first acoustic peak is material coming in and bouncing for the first time. The other ones are ones that have come down, bounced, and gone in and out. So the whole universe is kind of a big accordion. Doom, 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 doom. And so in really tiny sound waves, you have time to go bing, 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 20, 30, 40 times. And so you get a bounce there when they come, and then when they have turnaround points. And so you get a whole bunch of them, literally quasi-infinite number, but they have a very specific size based on how the universe is evolving during that time, and the constituents of the different pieces of matter. I'm sorry for this audience, it's going to be difficult to do any more than that, but it literally is that first peak is material coming down and then the pressure coming in and stopping the material. And so you get sound waves at a very specific size. That's the first one. The next one is in, out, and then you got in, out, in. The next one, in, out, in, out. So, and that way. Yep.
So here is a question there on the left.
Hello. Very nice lecture, sir. Sorry, I'm a bit of a dark matter skeptic myself. I wanted to ask it, how do you hypothesize dark matter? Because I think our entire perception of science is with our interaction with photons, and ironically, dark matter itself doesn't interact with photons, only with gravity. So how do you think we'll perceive dark matter in the future? Or do you think we need a mathematical revision of general theory of relativity?
So we have many hints of dark matter's existence from the gravity side of things. But it would be really nice to be able to see it interact. That has not happened. So I would agree that until we find interaction, there's always going to be some skepticism. But at some point, you're going to have to come up with something that doesn't predict properly, or B, a better alternative explanation. And those two things have not happened yet. And I cannot strongly emphasize how strong the measurements of the acoustic waves in the early universe are. Those, as I said, you tweak things even a little bit and they don't fit anymore. You tweak them a lot, and you get something completely different. So it's a very strong thing you got to get around. And when people go through and they say, I'm going to show that galaxy rotations are, my new theory can give you galaxy masses, right? I'm like, that's not the place to start. You want to start with the cosmic microwave background and then move to galaxies, because the cosmic microwave background is the Rosetta Stone.
Last question from the lady in the right.
Am I audible? Yeah. Thank you, sir, for the presentation. So in your presentation, you were mentioning about, different ways like in which people are trying to figure out the existence of dark matter. And in that, you talked about direct detection, and you said that we are having an underground mines, liquid xenon, and we are expecting dark matter to collide with it.
Yep.
My question is, why only xenon when we have so many other elements?
Say, what's the question at the end?
Why only xenon is used for
Okay.
this detection?
So the reason xenon is used is you want to not have any background. So the thing that xenon is, it is a one of a noble gas. So it has very low chemistry interactions. It is the heaviest noble gas that is not radioactive. So if you want to do radon, which would be even heavier and a bigger target, radon is highly radioactive. It's going to mess the experiment up. And so there's nothing else that really gives you the pure, no other background signals. And xenon, is heavy, 128 times the mass of hydrogen. And so it's the heaviest thing we have that hosts those properties. Okay. And it's liquid, so it's easy to do things underground with it relative to other things. If you were, for example, to have, imagine you put gold there, then when you get it turns out when it goes ping, you probably can't hear it, or you can hear it better in the xenon as well. So there's a reason why it was chosen. It's by far and away the best substance to do it. For a certain, should I say, for a certain set of types of dark matter. Okay? There are other models for dark matter. These are what we call weakly interactive massive particles, WIMPs. It's pretty good at doing that. If you have really tiny, like fuzzy dark matter, then it's not going to work. So it only works for a certain class of dark matter particles.
So I'm sure you all have a lot of questions, but unfortunately, we'll have to wrap up here. Please join me to thank Professor Schmidt for the exciting lecture. And I also thank the audience, both in this auditorium and online, for their presence and enthusiastic participation. I'd also like to thank the TIFR auditorium support staff, canteen, security, the science communication cell, and the public relations office for their support in a smooth organization of this lecture. There is high tea arranged outside. Please join us there. Thank you, everyone. Bye. Oh, that was fantastic. And I really liked that last slide, that iPhone slide.
Okay, yeah, that's a good one. I stole it. Someone else came up with it, and I've become the biggest fan. So, but I've got it.
Can you share?